Okay, we've seen that inside parallel plates the electric field is constant, uniform, directed from positive towards negative, and the voltage increases uniformly from its zero value at the negative plate to whatever positive value it is up here. The electric field, nice and straight. Now that's strictly only true for infinite plates. For finite plates there's actually a slight bulging of the electric field at the ends. But here in the middle it's nice and uniform, and the value of the electric field is just the voltage difference over the plate separation. Now we can do mechanics for charges that are inside a field. Having determined the electric field as voltage over plate separation, we could then find a force on a charge that's inside the field by multiplying the charge by the field. To see that that makes sense, notice that the units of electric field are newtons of force per coulomb of charge. And so therefore if you multiply by coulombs of charge, you get newtons. And then once you've got the acceleration, once you got the force, you could of course find the acceleration just by dividing the force by the mass, and then you can do kinematics. Another way to proceed with the analysis that's sometimes useful is energy. When you know the voltage or the potential, multiplying by the charge will give you the energy, the potential energy. That's because voltage is in volts, which is a joule per coulomb. So multiplying by coulombs, you get joules. Kinetic energy, of course, 1/2 mv squared, and then we could use the work energy theorem. As long as there's no external agents, mechanical energy will be conserved, so the total of kinetic and potential will be a constant. Let's look at a few problems quickly. So here we are accelerating a proton. This is a proton gun, you could call it. We just use a voltage to get the proton going really quickly. Now, if we want to speed up the proton, we're going to need to be repelling it. So this will need to be a positively charged plate, and this will need to be a negatively charged plate. If there's 1250 volts, we can, without loss of generality, say this plate is 0 and this plate is 1250. So, how could we find the final speed of the proton? Well, not knowing anything about the plate separation, we can't find the electric field and therefore can't do force analysis, but we can do energy analysis. We can say energy at the beginning plus work non-conservative equals energy at the end. Energy at the beginning, there's no kinetic because it's at rest, but there is potential energy. There's no gains or losses. At the end, at the 0 volt plate, the voltage is 0, therefore the potential energy is 0. It's all been converted to kinetic. So Q times the initial voltage equals 1/2 mvf squared. Now, you got to make your voltage V look different than your velocity V, because obviously they're different quantities. So putting in the charge, it's positive 1 fundamental charge, 1.6 times 10 to the power minus 19. That's the charge on a proton. And that's in coulombs. The voltage is 1250 volts, or joules per coulomb. And then that's got to equal, I'm running out of room, so I'll have to do it on the next line, 1/2 times the mass. Proton mass you can get off your data page, 1.67 times 10 to the power minus 27 kilograms, v squared. Solving for v, we get the speed of that proton, 4.89 times 10 to the power 5 meters per second. So you can get proton beams and electron beams going quite quickly. Now we're asked to express that proton energy in the convenient atomic electron volt units. Well, quite simply, I mean, we could take this energy, okay, and then convert it to electron volts, or we could just express the charge in e's and the voltage in volts. What do I mean by that? Well, this charge, the proton, is plus 1e, and it's at 1250 volts. So there's 1250 EVs of potential energy at the beginning, and therefore 1250 EVs of kinetic energy at the end. So because an E is 1.6 times 10 to the minus 19 coulombs, remember that an electron volt, or an EV, is this many joules. So that was energy analysis. And here's a problem that you could do either by force or energy. Let's make it a bit bigger. There we go. Okay, so we've got an electron that's moving, and it enters a set of plates. Now, this is going to have a small positive voltage, this is going to have a bigger positive voltage, and therefore this electron is going to get accelerated and it's going to be going faster at the end. Now we could again do this using energy, an energy solution. Let's just see what that would look like. I'll sketch the energy solution, and then I'll also sketch the force solution. So you'd say energy at the beginning, so it's got some potential energy because the voltage is 100, and it's got some kinetic energy at the beginning. There's no non-conservative work. Then at the end, it's got some potential energy and some kinetic energy at the end. So for the potential energy, it's QV, and the Q is minus 1.6 times 10 to the power minus 19. And then it's also got some kinetic energy, 1/2 mv squared. And we're told the initial speed is 5 times 10 to the power 5. So that's the mass of the electron. We had to go look it up. Now, the voltage is going up, but the potential energy is becoming a more negative number. So that's a loss of potential energy. And therefore, we're going to get a gain of kinetic energy. This is a velocity. If you work it out, it's 13 million meters per second. That's pretty fast. Now, if you did do it by force, you would first find the electric field in there. That's voltage over plate separation. It's actually the voltage difference. So we're going from 100 to 600. That's a 500 volt difference over a plate separation, which is given as a centimeter, I believe. Yes, 1 centimeter. Sorry about the scroll there. And so that is 50,000 volts per meter, or newtons per coulomb. We next find the force on this electron using QE. Q is 1.6 times 10 to the power minus 19, and this is the electric field. Then we find the acceleration by dividing that force by the mass of the electron. Or we can just put these two steps together. Put in the Q, the electric field, divide by the mass of the electron. And this gives a surprisingly large acceleration of 10 to the 15. Now, once you know the acceleration, you could just do physics 11. You can say its initial speed is 5 times 10 to the 5 plus 2 a d. This acceleration, 8.78 times 10 to the 15. The displacement is a centimeter, 0.01 meters, and then you'll get exactly the same speed that we had up there. All right, so here's a slightly different problem. So here we've got a proton moving at 2.5 million meters per second and entering this cascaded voltage region. This is actually going to stop the proton because we're gradually getting a higher and higher and higher voltage, and that means that there's going to be a repulsive force slowing the proton down. Or, put in other ways, you're increasing in potential energy and therefore decreasing in kinetic energy. Now, we're saying in which area will it stop? Well, we're asking, is it going to stop in this first region, the second, the third, or will it just keep on going and actually leave the plates? So how could we do that? Well, we don't know anything about the distances, so we're probably going to have to use an energy solution. So we're going to say that at the beginning, the proton way over here, 0 volts, far removed from these plates, and therefore it only has kinetic energy at the beginning. All right, the work energy theorem. So we're going to start with kinetic energy and no potential. Then the proton's going to come over, and do a little bit of foreshadowing here, it's going to reach over here and stop. At that point, it's only going to have potential energy. So 1/2 mv, this is a velocity v, equals qv, this is a voltage v. And so putting in the value of the mass of the proton, 1.67 times 10 to the power negative 27, and its velocity, then its charge for Q. Pause the video for a sec, work out the voltage, and then interpret that answer. I'll give you a moment to do that now. Okay, so hopefully you worked that out, and you found that the voltage when the proton stopped was about 32,600. Now, in plates, voltage increases uniformly with distance. So if this is a 30,000 volt and this is a 40,000 volt plate, somewhere 2,600 of the way between 30,000 and 40,000, so about here, that's exactly where it's going to stop, because voltage increases uniformly with distance. So we know it's going to stop in region 3. All right, let's try one final problem. So here we've got an electron, and then we're projecting it, so it's entering these plates. So this is somewhat like the previous problem. The electron's shot towards the negative plate, so there's going to be a repulsive force that brings it to a rest. So we could do this one using force or energy again. Let's start with a force solution. So first we find the electric field as voltage over plate separation, and then you find the acceleration and then figure out how far it goes. So pause the video and work through this problem, and then come back if you'd like to see my solution. The answer should be 3.05 centimeters, as the distance it comes to the negative plate, so it's going to travel about 2.95 centimeters. Or sorry, 1.95 centimeters. All right, so pause the video, try this problem yourselves. Okay, so presumably you've had a chance to do that problem. First, you'd find the electric field, 25 volts over 5 centimeters. Then find the acceleration. You get 8.78 times 10 to the 13. This is a slowing down acceleration, so when we go to do kinematics, we have to make it a negative number. And then you get that 1.95 centimeters. Problem finished. If you wanted to do it using energy, you would say that it's got kinetic energy and some potential energy due to the 25 volts, and then at the end, all of that's going to be converted to PE. So putting in the electron charge and the electron initial voltage, we see that's actually going to be a negative number, because of course the electron charge is negative. The initial voltage is 25. Putting in the electron mass and its initial velocity, you can find a final voltage of 15.3 volts. That'll be the voltage when the electron stops. You then need to convert that to a distance. So if it's stopping at 15.3 volts, this plate was 0, this plate was 25, how much distance is that? Well, we can just determine that using proportional reasoning. We can argue that, hey, the whole 5 centimeters of distance was a drop of 25. 25 to 0 was over 5 centimeters. So 25 to 15.3 was a drop over distance d. Solving for the distance d, you'll get exactly the same 1.95 centimeters. So that's a quick look at cathode ray tube physics and some simple warm-up problems.